Hi, I'm Adam Norris. I'm with the Mighty Peace Watershed Alliance, hoping to talk to you today about land use as a tool for watershed management. Obviously, this is not a new idea or anything groundbreaking, but I'm just going to tell you a bit of the story of my thesis. So, sat down to do my thesis. The first thing they tell you, right? Find something you're interested in. Okay, that's easy. There are lots of things I'm interested in. You know, I'm looking at things like land use, artic grayling, riparian zones, stream restoration, dissolved oxygen. All these things sort of interest me. And I got there and I got to be really muddled thinking, wow, I got all these ideas that are spread out. I got to pick one of them, right? And then it occurred to me to put them on a conceptual map. And as soon as you do that, it became clear to me that I'm just dealing with components of a watershed. So that helped me sort it out a bit. And I started to work on narrowing down the problem to a manageable scope. And I had the fortune to walk into the office of Craig Johnson, the senior fisheries biology up in Grande Prairie, and he helped me frame the problem. We sat down, we talked about this, and what he really was able to help me tease out is there are three components I was looking at. Land use, a water quality parameter, that is dissolved oxygen. I was really interested in the cycles. And then, of course, artic grayling. And more importantly, it was the linkages between them. So the relationship between land use and dissolved oxygen, and the relationship between dissolved oxygen and grayling. And could I connect all three of those dots? So I had a problem now that was in a manageable scope. So I was able to find a supervisor, Michael Sullivan. He's the provincial fisheries scientist. And we sat down and worked out a plan. What we did is we went to the Wapiti watershed, where there have been strong artic grayling populations, and we chose 9 sub-watersheds that had a range of land use. And then the local fisheries biologists went through and ranked these as to the artic grayling populations there. Red was extirpated artic grayling populations in these creeks. Green was scarce, so a population that was in decline or thought to be potentially in decline. And then blue was abundant artic grayling population, so they're doing very well. So we had that, and then I walked out of the meeting with Craig Johnson with $20,000 of equipment and went out to do things like measure velocity and calculate discharge, to look at riparian vegetation, channel characteristics, depth, width, the bed morphology. And finally, I launched a data sonde. The data sonde is a great thing. What it does is it takes continuous readings on a 15-minute or whatever interval you'd like, and I was able to track dissolved oxygen, temperature, and conductivity, and not even be there, right? So in this picture here, if you look under that yellow circle, you can see I've got my data sonde. What I did is I took it and I put it in a piece of PVC pipe with 2 holes drilled through it, wrapped it in chicken wire, nailed it with rebar to the stream bed so I knew where it was and it would stay in the water column, and then I cabled it to a tree on the shore. Part of that is to avoid the 3 great risks and dangers involved in field work: beavers, floods, and the souvenir collecting public. So, had that done, and then I had to do the challenging part. Summer went pretty well. I had to go out and do this in winter. At least the fisheries guys I talked to, they hadn't had a lot of experience launching these data sondes under the ice. Doing titration's no problem. People do it all the time. You chisel through the ice, do your stuff, you freeze your fingers, you go home. These probes are very sensitive, and once you get them calibrated, they're accurate. But if you don't get them calibrated properly, you're going to lose your data, or you're going to wreck the machine, which is expensive. So I would have to chisel a hole in the ice, run back to the truck, calibrate, launch, put this data sonde in a jug of water, put it under my layers of clothes, run back to the hole in the ice, stop through again, and get it under there without forgetting to put on the PVC and cable it so I wouldn't lose it. And that all went well, though. I didn't lose a data sonde, and I was happy to return all of them to Craig at the end of the time. So, just going to run through a bit of my data for you. A lot of those things I talked about that we did, the channel characteristics and stuff, that's essentially to look at whether I had comparable streams. Doing field work, there are no replicates. There's no way for me to go out there and get stream A and do it 3 times. So did I have streams that I can at least say are relatively comparable? If you look here, This is just one of the ones I looked at, stream depth. They're all in the same order of magnitude, and it's a variety across the three classes. So let's just say good enough to compare. Once I started pulling off the dissolved oxygen data, and I was really interested in this diurnal cycle, we got very classic picture here. X-axis is time, Y is dissolved oxygen. Yellow horizontal vertical line is sunrise, and the black one is sunset. So sun comes up, gets over the trees, the algae in the water, they start doing photosynthesis and pumping out dissolved oxygen. Oxygen levels go up. Just before sunset, the sun goes down below the trees, photosynthesis tapers off, and the algae start respiring. They pull that oxygen out of the water, so you get this nice cycle going, right? Very well known trend. So that's what I was seeing. Then all I had to do was figure out what it meant with all my 9 streams. Looking at, oh, that's nice, pretty graphs, lots of colors, lots of data. Start thinking about all the complicated stats tests that I'd learned in school. Can I use it? Well, now I have to incorporate temperature. So my mind's starting to look a bit like this. And I'm thinking, this is going to be ugly. And that's the real value in knowing smart people. Because smart people always make you look good. So I went into a meeting with Craig and Mike, and after an afternoon, my data looked more like this. On the x-axis here, we have mean summer water temperature. On the y-axis, that's mean dissolved oxygen in summer. Those ovals are centered on the means with standard deviation determining the size of the oval. So, perfect, right? I got a nice, lovely graph. There's a clear trend. The healthy populations of grayling are all up there along the top. The ones that don't have grayling, they look different. We know that dissolved oxygen is good for cold water fish. But something that I hadn't seen anywhere in the literature, and neither Mike nor Craig are aware of, is this interesting trend of healthy creeks having a large fluctuation in temperature. Something new. I don't know what it means, but I hadn't had anyone else write it down in the literature before, so I'm going to claim that as my own. And then the most important thing is that there's a trend. If you look at the shape of those ovals, creeks that are supporting grayling have a distinct dissolved oxygen and temperature regime. High dissolved oxygen, low fluctuation, high temperature, or lower temperature, but high fluctuation of that temperature. And when I started looking at it, it looked almost perfect, except for this one Steep Rock Creek. It looks like it should be supporting grayling. So I started thinking, what's going on there? And then I started thinking, it's a tributary to the Beaver Lodge River, one of the most impacted rivers up there. It has every type of fish migration barrier you can think of. Weirs, high runoff issues, low dissolved oxygen, and the last several years, it's just puddles of water, discontinuous puddles. So probably we're looking at a river that could support grayling, but is no longer connected to the population. So I was very happy with that. I've got a connection between grayling and dissolved oxygen. Could I now make a connection between the land use and the dissolved oxygen? So what I did to do that is I developed a phosphorus budget. And what was involved in that was essentially research, no field work. I went and drawing heavily on YEA 2006 and Mitchell and True 1992, I found phosphorus runoff coefficients for every type of Alberta landscape out there. Roads, hayfields, crops, feedlots, well sites, seismic lines, cut blocks, whatever. Took my GSI layers, broke out the hectares of every type of land use in the watershed, and then multiplied it by this coefficient. That gave me a theoretical phosphorus runoff for each watershed. And then to have something to compare to, I went and did a historical one, a pre-development one. Essentially, that involved taking these GIS layers and just pulling off every land use. Every road, every seismic line, every cut block, every subdivision, that all came off, and converted those back to the land cover of that area. So it might have gone back to a lentic area, or it might have gone back to a deciduous forest, depending on what the surrounding area was. And then I just took the ratio of that. The ratio of the phosphorus runoff currently to the ratio of that historically. And this is what I got when I plotted it. The x-axis is the increase in phosphorus runoff. this ratio of my theoretical phosphorus budget. And on the y-axis, we have two graphs. On the bottom part is the mean water temperature in summer, and on the top part is the mean dissolved oxygen in summer. I said, oh, that's a pretty clear, grouping. Can I make that fancier? And sure enough, to me, it looks like there's a bit of a break. Maybe it's a potential threshold. So I thought that could be my link going back from water quality up to land use. Can I do that for winter? Plotted those out. Looks very similar. And if I draw my line, I'm at the same place. Somewhere around a threefold increase in phosphorus, and a lot of things start to change for cold water fish and for dissolved oxygen. If you notice, I've got one creek that always seems to be hanging a little bit in between the two groups. So I'd like to talk about that a bit. Iroquois Creek is what I think is pretty unique, because in science we can't measure change. You go at one instant, you measure something, you go back at another instant, you measure it, and you infer change, right? We're not actually measuring change, we're measuring 2 points and inferring things. I think what's happening here is this creek is in the midst of that change. It was a artic grayling supporting creek, and now it's starting to move to one that might be extirpated soon. It's got a high phosphorus increase, and it's got low dissolved oxygen in the winter. So I'll be curious to see what happens with this. I collected reams of information. I really thought I was going to be looking a lot at, as I said, diurnal dissolved oxygen, nitrates, phosphates, ammonia in the water, roads, and a lot of those things didn't really show any strong relationships. And this is surprising because roads are the #1 proxy for land use. When you want to talk about land use, well, how many roads are there? Because you need roads for everything, from farming, for forestry, for oil, for houses. Everyone needs roads. And yet I have a very weak correlation. You can't really even say there's any connection between roads and in-water quality parameters, which indicates that there's more than one step in this connection between land use and this dissolved oxygen water parameter. There must be some other step in there because there is no direct correlation. So, can I make my pitch for a connection from land use through dissolved oxygen to Arctic grayling? I'd like to suggest that I can. Those land use areas that had this increase in phosphorus runoff, theoretical, always showed extirpated grayling populations above that threefold level. And that was those same creeks that had different dissolved oxygen regimes. So, my thought, and what I would submit to you today, is that there are a couple drivers here. And we can say, we can follow land use effects for the watershed through dissolved oxygen. And it's interesting because it's one parameter. And that, through phosphorus runoff, and that's what's driving dissolved oxygen in these creeks. So there's a couple of steps we have to follow before we even get to talk about cold water fish or Arctic grayling. So this was supposed to be a bit of a talk about watershed management. What does that mean for us when we're looking at watershed management? And I would ask you to pay close attention at this point, because otherwise when I leave here I'll be staked to an anthill. I don't know that we've been using riparian zones properly in watershed management. They're important, yes, but are they the drivers? I don't think so. I don't think we can go and say we're going to restore watershed health. Let's plant some trees in the riparian zone. Riparian zone are going to give you your biggest bang for buck for increasing water quality. But if we're going to look at managing watersheds, we got to go beyond riparian and look at land use. Riparian zones are only a fraction of what's on the landscape. And when I looked at my GIS stuff, I thought this is going to be a mess. Am I going to be doing a 30-meter buffer? Am I going to do a 100-meter buffer, calculating out all these riparian zones? And it didn't seem to matter. That small part of the landscape was overwhelmed by what happens on the bulk of it. So I think we need to be very aware of our land use practices. And when we think about riparian zones, we're going to be thinking about different things. We're going to be thinking about dealing with very specific problems, very localized problems, and I think that's their proper role. So I think Cows and Fish are a great organization, and they need to continue doing what they are. So please don't tell them that I'm saying they're irrelevant. So I'd just like to make a few recommendations out of all this. As watershed management people, we really need to look at appropriate scale. And that's going to be the watershed. It is a well-defined, functioning unit. And if we use that unit, we can make effective management decisions. And I would come back to riparian zones. They are a very effective unit of management for a local issue. But they're not a watershed scale tool. Then the next thing is, I started this looking at sort of perspective from the grayling side of things. Fish live in a world that is determined by things in a different universe. It's not what happens in the water that determines the quality of water. It's what happens on the land, something in a totally different realm. And if we want to manage water or watersheds, we're going to be leaving groups like this, and we're going to have to be doing a lot of work to engage everyone across the landscape. That's regulators, policymakers, educators, government, industry, NGOs, and somehow we have to make sure we can get engagement across the whole board because everyone is on that landscape, and our land use on that landscape is what's driving the watershed. And finally, this one I really like, number 3. It sounds like a medieval curse. Be wary of a 3-fold increase in phosphorus. I can't tell you this applies everywhere, but I can tell you up in the boreal forest of northern Alberta, more than 3-fold increase in phosphorus is really bad for cold water fish. So I'll just run those 3 points by you again. Use appropriate scale of management, engage as widely as you can, and really watch if you get a 3-fold increase in phosphorus.